On the morning of May 25, 2025, a critical logistics corridor in the Indian Ocean was abruptly disrupted. The massive MSC Elsa, a heavily loaded Liberian-flagged container ship, took a severe 27-degree roll to starboard. Unable to recover, it sank 51 meters to the seabed, dragging 640 shipping containers down. The immediate result was a sprawling ecological discharge. The wreck released hundreds of tons of toxic bunker fuel and millions of pre-production plastic micropellets, known as nurdles, which coated the Kerala coastline. This typographic layout of the Pellet Pollution Index formula demonstrates how marine biologists measure the density of plastic pellets per square meter. The data from the Elsa 3 spill pushed local beaches past the threshold of 3,000, placing the contamination firmly in the very high danger category. Initial rapid response assessments attributed the sinking to a single technical malfunction in the ship's ballast tank. But preliminary investigations from India's Directorate General of Shipping pointed to a deeply embedded systemic failure. A fully certified operational container vessel on a routine coastal transit does not spontaneously capsize. To understand what happened, we must reverse engineer the mechanical timeline of the Elsa pre. The evidence shows how ignored physics and a regulatory culture of paper compliance turned a certified vessel into a massive environmental hazard. The sequence of failure started before the ship even left the Vizhinjam International Seaport. Port authorities logged a persistent 5 degrees starboard list during cargo loading. The ship's operators dismissed the warning. The 28-year-old vessel was operating with severely compromised watertight integrity. It had struck a bulk carrier off the coast of Yemen in 2016, and the underlying structural damage was never fully repaired. Hydrostatic pressure forced its way into the hull through 2 failures, a leaking manhole cover on tank number 5 and a cracked weld seam on the port wing tank. Because internal bulkheads were compromised, progressive flooding bypassed containment, pooling directly into cargo hold number 4. Modern container ships manage this type of list using an automated integrated healing correction system. When sensors detect a tilt, the system automatically pumps ballast water to the opposite side to keep the ship level. On the Elsa 3, this automated healing system was entirely out of commission. The ship's diagnostic sensors actively flagged the danger. The ballast management system registered abnormal pressure readings continuously for 36 hours before the severe list developed. Both the onboard crew and the shoreside management team left these critical alarms unaddressed. This occurs through the normalization of deviance. When a crew is forced to operate degraded machinery over a long period, constant warning alarms are treated as normal background noise, right up until a catastrophic failure occurs. With the automated system dead, the crew attempted manual ballast corrections, but the primary ballast pumps and actuator-controlled valves were heavily defective, leaving them physically unable to counterflood the port side. This demonstrates the free surface effect. As water pools and shifts inside the starboard hull, it acts as a dynamic weight, dragging the center of gravity off-center. This mass eradicated the metacentric height. Past a 26-degree angle, the vessel's righting lever collapsed entirely. Deprived of stability, the hull rolled sharply. Gravitational shear caused the container stacks to tear loose from their lashings, sending them plummeting into the sea. Below deck, the progressive flooding finally breached the ship's most vital compartment, the engine room. The inundation of the generators triggered a complete electrical blackout, turning the Elsa 3 into a dead ship. Stripped of internal power, the crew lost any remaining ability to operate the emergency bilge pumps. The chief officer had joined the vessel just 1 week prior, and the multinational crew had no practical, real-world training for executing manual system overrides during a pitch-black blackout scenario. The physics of the free surface effect pulled the hull down, but human unpreparedness sealed its fate. A manageable structural leak became an unrecoverable capsize. To understand why a ship was legally permitted to sail in this state of decay, the investigation moves from the ocean floor to the corporate boardroom. 8 months prior to the sinking, the Elsa 3's crew submitted formal requests for critical spare parts to repair the failing healing and bilge systems. The operational management company in Cyprus ignored the requisition, forcing the crew to sail using temporary mechanical patches for nearly a year. This timeline charts the Elsa 3's global inspection failures between 2015 and 2024, revealing a long track record of detentions. Zooming in on Abuja and Tuticorin, the data shows recurring clusters of critical safety defects, firefighting faults, heavy engine room oil, and failing life-saving appliances. This pattern exposes the practice of paper compliance. A vessel meets the strict documentary requirements to pass audits, while the physical reality of the hardware continues to fail. The final regulatory safeguard failed. Despite the obvious physical decay and the extensive history of detentions, the Classification Society Bureau Veritas certified the Elsa III as seaworthy until 2028. Furthermore, the vessel was registered under a flag of convenience in Liberia. This legal structure deliberately fragments ownership and operational command, creating a liability shield for the parent operators. Maritime legal experts argue this framework allows a systemic breakdown of international conventions that were specifically designed to protect coastal states. The Elsa III reflects a broader industry trend, where shipping operators intentionally cascade their aging, highest-risk vessels into global south markets, where regulatory enforcement capacity is often weaker. The sinking of the Elsa III reflects a broader culture of cost minimization, where critical maintenance is deferred and operational risks are shifted onto the coastal environment. The loss of the MSC Elsa III was a fully preventable failure, resulting from a chain of technical and management neglect. Deferred maintenance compromised the hull, ignored diagnostics killed the ballast system, and a lack of training turned a blackout into a capsize. The disaster immediately disrupted the regional Vizinjum to Kochi logistics network, while initiating a catastrophic long-term environmental contamination. The physical evidence of that contamination remains embedded in the shoreline. Millions of these plastic nurdles represent a permanent toxic scar on the livelihoods of local artisanal fishing communities. While salvage divers extracted the ship's bunker fuel, the highly reactive chemical cargo, including calcium carbide, was left abandoned on the seabed 51 meters below. That abandoned cargo creates a silent, multi-generational threat to the Arabian Sea's benthic ecosystem. Global regulatory bodies must recognize this disaster as a mandate to prioritize rigorous physical inspections over mere documentation reviews. Until the paper compliance loophole is permanently closed, aging maritime fleets will continue to pose a foreseeable risk to the world's coastlines.